All right, well, welcome back, everyone. In today's video, we're going to go ahead and discuss Introduction to the Engineering Design Process. So, goals for today's video. First, we're going to look at a case study. You might remember hearing about Boeing's 737 MAX. And this is an example of a situation where the engineering design process didn't go as it should have, and mistakes were made. So sometimes a good way of learning a process correctly is by learning from our mistakes. And so we'll first review this case study about Boeing's 737 MAX and see what we can learn and apply to the engineering design process. Then we'll go ahead and review the engineering design process itself. And we'll see how we can apply the steps of the engineering design process in order to solve problems. So let's go ahead and get started. Let's go ahead and try a quick review question. And here we are looking for the following statement that is not a good practice to follow when using critical thinking. You'll remember last time in our previous video, we talked about ways to improve at problem solving. So see if you can remember, which of these is not a good practice to follow when solving problems? So what do you think? In this case, the correct answer here is choice A. So critical thinkers are very careful about how they solve problems. So you don't want to just jump in blindly and try to solve the problem as is. You want to take time to plan, review your data, and understand the problem. So choice A would be not the best practice to follow. Choice B, C, and D are all good practices that we want to follow in critical thinking. So let's keep our critical thinking skills and problem-solving skills from our previous video in mind. And we'll see that the analytic and creative problem-solving skills we've learned are still very relevant to the engineering design process. So let's go ahead and first look at this case study with the Boeing 737 MAX. And we'll use this case study to help us understand why the engineering design process is so important. So a lot of this information that we're going to share is not information that I require you to learn for this class, but I do think that it gives us a lot of good context about the engineering design process. So if you're curious about the Boeing 737 MAX and you want to learn more, I would encourage you to look at the references that I've linked to in these slides. I'll also share the links in the description. So if you want to take a look at these references in more detail, you're welcome to it. So once again, I don't expect that you memorize the Boeing 737 for the purposes of an exam, but let's focus on what we can learn from this case study. So you may remember seeing this news headline. The U.S. House of Representatives released a report stating that the Boeing 737 MAX crashes that happened were the horrific culmination of a series of faulty technical assumptions by Boeing's engineers, a lack of transparency on the part of Boeing's management, and grossly insufficient oversight by the FAA. FAA here is the Federal Aviation Administration. So clearly, some mistakes were made in the case of the Boeing 737. So let's take a look at what we can learn from this incident. So first, a little bit of background. You may remember hearing about the Boeing 737 MAX. This was a brand new passenger airplane made by Boeing, and it was a top-selling passenger plane. However, after it was released to the market, there were 2 plane crashes in a 5-month period of time. And so this started to raise eyebrows, and people wondered, was something else causing these crashes? And so for a period of time after the plane crashes had happened, the 737 MAX planes were grounded, pending evaluation of safety concerns. And unfortunately, these 2 plane crashes caused all the passengers on board the planes, as well as the crew, to lose their lives. So this was a really tragic incident that happened. And as we'll see, unfortunately, these crashes may have been preventable. So let's review a little bit of background. And here I'm just summarizing the information available in these references. So if you'd like more information, I'd encourage you to take a closer look at the sites I've linked here. Basically, the Boeing 737 MAX was considered to be a very high-efficiency aircraft, and it was designed to fly further and more efficiently than its predecessors. And part of the reason for this was because Boeing had implemented some design modifications that improved fuel efficiency and range. But it turns out those design modifications are also suspected to be the cause of those 2 plane crashes. You can see in this nice figure there were a lot of improvements made to the Boeing 737 MAX, and a lot of these improvements were all focused on improving the efficiency, making the aircraft quieter, more comfortable, and also allowing it to be overall a longer range, more efficient aircraft. So here's one of the key design changes of that 737 MAX. So as part of the design changes, the engine position was adjusted. And this new engine position changed the center of gravity of the aircraft. And the problem with this was that the nose of the airplane could potentially pitch upward during flight. And for a jet engine, if the nose pitches upward, then the jet engine could stall, and that could create some serious problems. And so to prevent the plane from stalling and the nose from pitching up, Boeing implemented some software called MCAS, or Maneuvering Characteristics Augmentation System. And this software was supposed to automatically trigger if the nose started pitching too high on the aircraft. The idea was that this maneuvering system would automatically push the nose of the aircraft downward if we started pitching upward by mistake. So Boeing had good intentions with this software. They designed it to be a safety precaution. They didn't want the engines to stall, they didn't want the nose to pitch upward. So the software is supposed to make the plane safe. So here's the problem with that MCAS system. The system relied on a single sensor to provide data. This sensor was called an angle of attack sensor, and the idea was that angle of attack sensor should tell us what our angle of the plane's nose was, and ideally, if we tipped our nose upward, then we would automatically correct for that. But here's the problem. We were relying on just one sensor to provide data to the system. And if that single sensor failed or sent bad data to the system, that MCAS system could activate by mistake. And so if you look in these figures from our references, you see that that's likely what caused our planes to crash. Basically, what was happening is that sensor may have caused the MCAS system to trigger by mistake, causing the planes to crash. So what investigators were able to determine was that pilots in both crashes got confused when the MCAS system kept activating repeatedly. And because the system was tied to a single sensor, failure was more likely. Thankfully, Boeing has since redesigned this feature so that the MCAS system has redundant sensors, and so it's much less likely to malfunction. So what can we learn from this whole process? Well, the MCAS system relied on a single sensor, a single data point. And that faulty data from the sensor likely caused 2 plane crashes and over 300 people to lose their lives. So a really big important lesson we can learn is to never ever allow something to have a single point of failure. We don't want to rely on just one sensor or just one data point. As much as possible, we need to have redundant sensors and multiple data points to guide our decisions. Another thing we can learn. It turns out that the chief project engineer approved a critical design change to the software even though that engineer was unaware of key details. So the engineer signed off even though they did not know the full details about how that software worked. That chief engineer was also unaware of a warning from a test pilot. And a test pilot who knew about that system warned that if the system malfunctioned, the results could be catastrophic. And so it's unfortunate to see that Boeing and FAA, they could have caught these flaws in the flight control system during the design stage. And I'm not saying that this justifies the mistakes, but it was also shown that the Boeing employees were driven by pressure to get the new planes to customers quickly. And they also had pressure to deliver those planes without requiring pilots to undergo retraining. And this goal was such high pressure on the employees that they had countdown clocks on the wall of a conference room. And once again, this is not something that only Boeing will experience. Having been an engineer in industry, I can tell you that there's going to be pressure to meet deadlines. There's going to be pressure to get your product to customers quickly. And while that pressure can be a good motivator, you also don't want that pressure to cause you to rush and make mistakes. And so it's something you need to be very mindful of, and that we can definitely try to learn from this situation is that we need to make sure, yes, it's important to get our product to the customer, but we need to do our due diligence to make sure that product is safe. And finally, this report stated that Boeing had multiple missed opportunities that could have shifted the trajectory of the design and development toward a safer course. So the House report concluded that there were many missed opportunities throughout that design process, which caused these tragic events. So with these lessons in mind, let's go ahead and continue on. And now let's take a closer look at what the engineering design process actually is. And let's keep these lessons in mind to see how we can make sure that we make our best possible effort to follow our engineering design process in a safe and effective way. So first, let's start out with a definition. What is engineering design? You may remember from our earlier videos, we talked about ABET. ABET is the Accreditation Board for Engineering and Technology. ABET gives accreditation to engineering education programs, and ABET defines engineering design as the following. Engineering design is the process of devising a system, component, or process to meet desired needs. Engineering design is a decision-making process, often iterative, in which the basic sciences, mathematics, and engineering sciences are applied to convert resources optimally to meet these stated needs. So that's a fancy definition. And for us, let's focus on these three key takeaways. First, engineering design is a process involving decision-making. Also, engineering design can be iterative. That means we may need to repeat the process. And also, engineering design involves applying sciences to solve problems. So remember, our focus as an engineer rather than a scientist or technician is our goal is to apply sciences to solve a specific problem. It's also interesting to look at an older definition from ABET. ABET also used to have the following in their definition. They stated, although the fundamental elements of the design process are the establishment of objectives and criteria, synthesis, analysis, construction, and evaluation, notice what they say here. It is essential to include a variety of realistic constraints, such as economic factors, safety, reliability, aesthetics, ethics, and social impact. So we can get some additional takeaways from this older definition. Notice additional constraints, such as our economic factors, safety, reliability. These factors must be considered. We saw in the case of Boeing 737 MAX that the design was probably rushed and most likely not enough consideration was given to these other factors. Also, second takeaway, ABET emphasizes that design should keep human interests and benefits in mind. So again, we're trying to focus that at the end of the day, we should make sure that our design is going to be safe and it's going to be keeping human interests in mind. We do not want to release a design that could be dangerous or cause people to get hurt. So before we jump into the engineering design process, let's also review a few more important things to consider. The first thing to consider is that Many of us are new to engineering, and so please don't be intimidated by this process, especially the first few times you do it. Everyone starts as a beginner. And the best way to learn engineering design is by doing it. Just like with problem solving, learning by doing is really important. Also, seek to understand and think critically. Remember those problem solving strategies and critical thinking strategies that we covered in our previous video. These strategies are also useful when we work on the engineering design process. This third point is also really important. In school, we often solve problems where there's a very clear-cut answer, or where there is a perfect solution. But in the real world, you're not going to have everything perfect every time. It's possible that none of the solutions will be perfect. So you want to do your best to find the best possible solution, but give yourself permission to make mistakes and learn as you go. You'll find in the real world, not everything's going to be perfect. It's not possible to have perfect. You do the best you can to get the best solution, but it's okay to not have everything perfect, especially the very first time. Next point, failure is a part of the design process. It indicates that the current solution needs to be and can be better. Once again, failure is a part of the process. What this also means is that we need to be patient. And we need to be able to pick ourselves back up and persevere. So even in the face of problems, we need to be patient and be able to persevere. So you're not going to necessarily hit a home run every time you try engineering design. There's going to be ups and downs. There's going to be things that work and things that don't. And so being able to embrace failure, learn from failure, and persevere is really important. And notice we even say that in the next point. Engineering design is iterative, time-consuming, and frustrating. I'm saying this not to scare you, but to be realistic. If you want a career path where everything works the first time and you get instant gratification, engineering might not be that path. Solving engineering problems can be incredibly time-consuming. Problems can take months or even years to complete. So you have to be incredibly patient. When I was in my first engineering role, one bit of advice I received was to grow a thick skin. And what you mean by that is to not take stuff personally, but to understand that there's going to be ups and downs, and you need to be able to be patient and power through even when the process is frustrating and challenging. Next point, communication and teamwork are essential. Later in the course, we're going to learn more about strategies we use for communication and teamwork. We'll see that projects are big and complex, and you're going to have to collaborate between many people. And, of course, people don't always agree. People don't always communicate well. So, we'll discuss communication and teamwork more later on. So as we jump into engineering design, keep these points in mind. This stuff is challenging, and everybody has to start somewhere. And even very experienced engineers are still learning and growing. So be patient with yourself and give yourself time to learn this process. So let's go ahead and look at the 5 main steps of the engineering design process. One thing I'd like to point out is that depending on who you ask or what textbook you look at, the steps of the engineering design process may vary. Typically, they all kind of are approximately the same. These 5 steps are the ones that are highlighted in our textbook, Engineering Your Future. So, for our purposes, we will follow the steps shown here. So, our very first step is actually what I call step 0, assemble the team. So, believe it or not, before we even start with define and imagine, we need to put together our team. And so what we do is we appoint a project manager to coordinate the team's efforts and manage the schedule and tasks. Later in the course, we'll learn more specifics about project management. Projects may also include a technical lead, and so their job is to oversee the engineering decisions. Another point to consider is that teams are usually kept small initially. And as the project makes progress, more team members may be added. One other thing to think about is that if you work in engineering industry, you're likely going to be involved in more than one project at a time. So often you'll need to juggle between different projects depending on your priorities. Let's go ahead and do a very quick tangent on project managers. Many students are unaware that project management can actually be a very interesting and rewarding career path. If you're one of those people that has really good organizational and people skills, you might make a really good project manager. Project managers are interesting because they manage the schedule of a project. Their job is to oversee all the tasks that need to happen and ensure that project completes on time. So project managers are really good at finding bottlenecks and contingencies within a schedule and helping everybody ensure the project is completed on time. Project managers spend a lot of time in meetings and discussions to help the team prioritize and complete tasks. And if you're not in a meeting, you're probably going to be updating your spreadsheets and schedules to keep track of all the different tasks and status updates. One thing to note about project managers is that they have very limited influence on design decisions. Their focus is primarily on the schedule of the project. But the cool thing about project management is you get to see the entire engineering design process from the very beginning through to completion. And you can manage a schedule that contains hundreds or thousands of tasks for every step of that process. One other thing to note is that you don't necessarily need a ton of engineering expertise to be a great project manager. Some of the best project managers I worked with did not even have an engineering degree. They were just really good at organizing and planning. However, having an engineering degree or an engineering background is often really desirable. So I don't expect you to memorize these points for the purposes of our first exam. But just in case you're curious, you might want to consider project management if any of these things sound interesting. All right, so with that, let's go ahead and move on to the actual engineering design process. Step 0 was to assemble our team and appoint the project manager. Let's move on to step 1. Step 1 of the engineering design process is define. Notice the similarity between this process and creative problem solving. In the define step, we need to clearly define our problem. We also want to ask ourselves what is known about the problem, and we want to identify our working criteria or goals that we want our solution to meet. One thing to note about this whole process is that many companies and industry have their own versions of a product development cycle or product life cycle. And so you might see when you go to work for a company that you'll follow these same rough steps, but they might have slightly different names and different milestones that you complete during the process. All right, so let's talk more about what happens in the define step. So in define, our task is to clearly define and understand the problem. This might seem a little simple and basic, like, isn't it obvious what our problem is? But believe it or not, defining the problem is a crucial step. It points the team in a particular direction. If you have a poorly defined problem statement, it can result in wasted time and resources. So often at the beginning of the process, sales and marketing teams might be involved. That's because we want to make sure that our solution meets the needs of our customer. Here's one example of defining the problem. In the hardware industry, they actually have these specifications called MSAs, or multiple source agreements. And sometimes what happens is we put together these agreements which have set requirements for products. And so many companies and customers will meet together and decide on these requirements. Once everybody decides on the requirements the product must have, each company needs to follow these specifications. And this ensures that products are compatible with each other and that the customer's needs are met. If you think of things like USB, for example, or Wi-Fi and internet protocols, a lot of these tools actually used MSAs to help ensure that the problem was clearly defined. Another part of the define process is asking, what is known about this problem? You may remember in some of our previous activities, we learned about how to do research. This is one of those situations when an engineer may need to do some research. So we look at what information is available about our problem. And so we might review books, publications, maybe research, university journals, maybe patents, professional associations, trade journals, newspapers and magazines. In some cases, we might even disassemble the competitor's product and do reverse engineering. Of course, if you do that, you need to be careful of potential ethical issues, but it can and sometimes does happen where people will take apart a competitor's product and examine how others have approached the problem. So there's some additional questions you want to ask yourself when figuring out what's known about the problem. You also want to look and see, is a solution already available? If yes, who's making it? What are the advantages and disadvantages? How is it made? What is the cost? Was the solution well received? What if a solution is not available? A good question to ask is there a reason why that solution's not available? Did someone try and fail? Very important to understand, if nobody's done something before, want to make sure there's not some catastrophic reason why. The last part of the define phase is to establish what's called working criteria. Working criteria are preliminary goals. The purpose of working criteria is to help you validate and down-select possible solutions. You can use working criteria to figure out which design idea is the best solution. These criteria may change as the project progresses, but notice there's a lot of different criteria we might be thinking about. Depending on the customer's needs, cost might be a big one, manufacturability, size, weight, strength, appearance, aesthetics, ease of use, and so on. So there's many possible criteria that we need to think about in our design. Another thing to think about is this term DFX. DFX is an acronym for Design for X, where X could be manufacturability, could be testability, could be cost, could be variability or power. So as we design our product, we might want to think about how easy will that product be to build or to test. These might be considerations that we include in our working criteria. So real quick, before we move on, let's try a practice question. Go ahead and pause the video for a moment and see if you can find the statement which is not correct about step 1 of our design process. Go ahead and give it a try. All right, so what did you come up with? Correct answer here is actually choice A. It's not okay if our problem is poorly defined. Sometimes more information comes available and we realize we need to tweak our problem, but ideally, as much as possible, you want to have a very clear problem statement and definition of your problem. If your problem is poorly defined, we saw that could lead to cost and delays and other problems. We want to make sure that our whole team understands what the problem is that we're trying to solve. So the incorrect statement is choice A. All right, let's move on to our next step. Step 2 of our engineering design process is imagine. And so in this case, this is where we try to develop as many solutions as we can. Remember, the goal here is to just imagine. Come up with that list of solutions. We worry about picking the best one later. In the imagine step, we just want to brainstorm and come up with a big list of solutions. And so you may remember in our previous videos, we covered some brainstorming techniques. So you could use those techniques and also take a look at some of the techniques in Chapter 7 of Engineering Your Future. Once we have completed the imagine phase, the next step is to evaluate. So during the evaluate stage, we evaluate the best ideas that we came up with during the imagine step. So during the evaluation process, we do some early elimination to decide the best idea. So initially, we want to come up with a short list of ideas that we think are best. Initially, we might just eliminate duplicates, identify duplicates, and have people vote. If there's a lot of potential solutions, we might need multiple rounds of elimination. And I can tell you from firsthand experience, sometimes we don't have enough information to choose a single best solution. So sometimes teams will decide to pursue slightly different designs in parallel at the same time. And once more data is available, then we make a final decision. So during evaluation, your goal is to go through and choose your best ideas that you want to continue in the design process. Here's a few more things to consider. Any leading solution that we come up with during the evaluate phase, we need to make sure that solution will work, or that it has strong potential to work. So every leading solution should undergo thorough technical and financial analysis. Often this is where those analysis engineers come in. Analysis engineers can help us run simulations and analyze data and figure out how likely our ideas are to be successful. So during this evaluation stage, while we analyze the technical financial aspects, we consider engineering principles, simulations, estimation, analysis with compatibility of other criteria, for example, cost or manufacturability. We can also look at whether our results are reasonable, and cost is often a big factor as well. Can we actually build this idea at a reasonable cost within our targets? And sometimes we just don't have a lot of data available this early in the game. So sometimes we need to make assumptions and build in buffer and safeguards until we know more data. Let's go ahead and try another practice question. See if you can identify here which of the following statements are true about the imagine and evaluate steps. Go ahead and pause the video. See if you can identify the true statement. All right, so what did everybody think? Which of the following statements are true? Let's first identify the false ones. Choice A is definitely false. Remember, we do require thorough technical and financial analysis. Also, choice C is false. As we mentioned, we can have multiple rounds of elimination as needed. Choice D is also false. When evaluating solutions, we do need to worry about cost and other factors, as well as the laws of physics. So the true statement is choice B. All right, so after evaluate, our next step in the engineering design process is create. In the create phase, we create models to help us visualize, develop, and even test our design. And so, depending on what we're trying to build, many different kinds of models can be used. Here's a few different kinds of models we might make in the create phase. If our product is relatively small, we might make a full-scale model or a prototype. These are sometimes called mock-ups, so this is literally an actual size version of your product. For very large products or very large solutions, we might make a scale model instead. A scale model simulates the design, but it's a model that is not actual size. So often this is used for very large structures like dams, highways, bridges, big buildings. This can help us simulate our design, but at the end of the day, it's not a full-size actual product, it's an approximation with a scale. Another type of model is diagrams and graphs to help us visualize our data and particular features. Another tool that we're going to learn later on is computer models, such as CAD, or computer-aided drafting and design. Computer models can help us transform our ideas into actual 3D models, and depending on what we're trying to build, we might even 3D print or fabricate individual pieces. Also, we might choose to make mathematical models. So for very complex systems, or for systems that have a lot of stuff going on, mathematical models might help us understand our system. So once we've created our models, our next step is step 5, the test phase. We need to perform tests on our models. Tests are performed to make sure that our ideas meet the required criteria that we defined. Testing is extremely important. Testing allows us to check whether our working criteria are met and whether this design is making progress against our goals. You might remember the test function of engineering. That is a function that is common across all types of engineering. That's because every kind of engineer will need to test their design at some point to verify that it is meeting the requirements. And of course, depending on those test results, we may be finished, we may need to go back and make changes. So depending on the thing that you're actually trying to design, many different kinds of tests could be performed. Here's a list of just a few of the many tests that might be run. First is function. How well do we actually fulfill the intended role? There's form. Does our shape, size, and weight help us accomplish our task? Safety is another big one. Is the product safe? How about ease of manufacture? That's really important. How easily can this product be built? If we can't easily build it, it might be really hard to sell at a reasonable cost. Other tests might include strength, reliability, and durability. So again, how likely is this thing to fail? How reliable is it? How long will it last? Also, end of life. What do we do with the product when it stops working? Could we recycle it? Also, quality consistency. How consistently can we fabricate this product? Maybe there are certain parts of the product that are more difficult to fabricate within a given specification. So depending on the complexity of our product, we might need to be mindful of repeatability and consistency of the quality. And finally, consistency of testing. You want to make sure the tests you're running are actually reliable and consistent. A test won't do you any good if the test itself is not consistent. So once we've performed these tests, we might still need to decide on what design is best. So to help, we sometimes use what's called a decision table. The idea with a decision table is we assign points to our different working criteria. So essentially what we're trying to do is visualize and rank how each model performed in our different tests. And typically we weight the performance based on how important that working criteria was. So in this example, safety had the largest weight with 15 points available, whereas cost and recyclability did not have as many points possible. So this caused safety to be weighted more strongly than the other factors. And you can see, for example, in this decision table, we see that option 3 was our highest scoring design because it had the highest overall point total. Let's go ahead and do another practice question. Here we are looking for the statement which is true about the test phase. See if you can find it. All right, well, let's go ahead and start by eliminating the false statements. Choice A is definitely false. We always need to run tests. We want to be completely sure that our design is going to meet our requirements. Choice B is true. Tests will allow us to check whether our working criteria are met. C is also true. Based on the results, we could adjust our design. D is also true. We can use decision tables to help us rank each option. So correct answer here is choice E. So now let's talk about what happens at the end of the engineering design process. As we mentioned, the engineering design process is iterative, meaning it can repeat. So depending on our test results, we might need to go through the engineering design process a few times until we get all the design optimized to our requirements. The outcome of our design process, so the end result should be a design ready for implementation, meaning we have a design ready to give to our construction or manufacturing team and ready to transition to manufacturing. We want to make sure that design is ready to go to manufacturing because we don't want to have to make design changes after we've started our manufacturing process. Design changes during manufacturing can be incredibly costly to implement, and they almost always cause significant delays. So you want to make sure that you work closely with the manufacturing team even during the design process. We see that design and development team members work closely together during this whole engineering design process. And the reason for this is because we want to ensure a smooth transition from design into manufacturing. We want to make sure that once that design is finished, the manufacturing and development teams are confident that they can effectively produce that design. Another important result from our engineering design process is documentation. You might be thinking, well, wait a minute, Professor Erickson. I'm not an English major. I don't want to write stuff. What's with this documentation thing? It turns out that documentation is an extremely important part of an engineer's job. Documentation is our way of communicating what our solution is. We need complete, thorough, and transparent documentation and reporting. This is necessary because we need to take our design and give it to our manufacturing team and the rest of our team. We need other people to look at our design and know how to fabricate it and know what our requirements are. So our documents will include specifications and drawings for each part and the entire product. We will also have specifications for materials and suppliers. There may be reports, drawings, and data documenting successful completion of our design process. And the development team is also going to need to figure out what equipment and processes and components are needed for manufacturing. So once again, strong communication between the design team and the development team is extremely important to ensure a smooth handoff from the design team into manufacturing. Once the engineering design process is complete, additional team members may become involved with the product. You may have more managers and supervisors involved as the amount of people on the team gets larger. You might also have more technical representatives. You're starting to manufacture your product, you're starting to market it to customers, so more technical staff might be on board. And there might be more business representatives on board. You'll have managers, maybe HR and finance, to manage team and budget. Also, purchasing becomes more important. If you need to purchase large amounts of raw materials and components, you need to have purchasing personnel to help manage purchasing of all the materials you need. Also, marketing, advertising, and sales are needed to sell the product. And you also need attorneys and legal staff. So lots of people will become involved with your project as the engineering design process finishes. So let's go ahead and wrap up here for today's video. So now you should be able to understand how the engineering design process works. And let's also keep in mind what we can learn from Boeing's 737 MAX situation and from other engineers who came before us. Make sure you're also comfortable describing the steps of the engineering design process and start thinking about how we can apply these steps in order to solve problems. We'll take a closer look at the engineering design process and some examples in our next video. Thanks everyone for joining the fun, and we will see you in the next video.